Lesson 20, falling down. First pause the video and do the warm-up problems, and then in a moment I will show you the right answers. Please pause the video right now, do the warm-up problems. Here are the answers. Please remember that for number 3, there are no official definitions of science. This is just the definition that I'm running on. It's my favorite definition. So it's going to be the correct answer for all of our quizzes and tests. You might see other definitions by other people in other places. Number 4, then, what can science study? Well, I suppose one way of answering it is it studies matter and it studies energy. But here's another way of putting it. You cannot study good, bad things, whether something is a good piece of art or a bad piece of art. You cannot study if a law or a philosophy is the right thing or the wrong thing. That's not science. That's going to be another area of study like philosophy. You cannot study the supernatural. That's not something that is matter. It is not energy, and so therefore it is not science. Number 5, limits of science, not infallible, meaning it is not mistake-proof. Science makes mistakes all the time. We just hope that it self-corrects and that people find mistakes and eventually correct them. But there have been some mistakes that have been believed for hundreds of years. So it'd be surprising, or it would not be surprising if we found out that stuff that we believe today is completely wrong. Next, it is not omniscient. We cannot know everything about the universe. It just physically is not possible. Please spend a moment to read the main ideas of the last lesson, today's purpose, relevance, success, today's grades, and the next quiz. Notes. A long, long time ago, it was the predominant view that the heavier the object, the faster it would accelerate as it falls. In fact, a lot of people believe that today. I would imagine that at least half the class in my physics room right now believes that the heavier the object, the faster it falls. Galileo is credited with proving that the acceleration due to gravity, in other words, the acceleration of a free fall, is the same for all falling objects. Number 2, in the metric size system, the size of the acceleration is 9.8 meters per second squared. Perhaps I should include in that the negative sign because the force of gravity is downwards, and so the acceleration it causes is negative. In the English system, it is negative 32 feet per second. In this class, we're always going to be using the negative 9.8. I just want you to be aware of the 32 in case you go to other websites and they have the different units. Number 3, if an object is initially stationary and dropped, its velocity after 1 second, 2 seconds, and 3 seconds are the given values. Now remember, stationary means that the initial velocity is 0. After 1 second, this acceleration here of negative 9.8, that tells us we changed the velocity by negative 9.8 meters per second for every second that passes. So if we start off at 0, change that by negative 9.8, we get negative 9.8. After another second, we change it by another negative 9.8, and it becomes negative 19.6. After another second, we change it by another negative 9.8, and we get negative 27.4. After another second, it'd be 36.2. After another second, 45.0, I guess, or something like that. I lost count. Okay. The size of the acceleration is used in lots of situations in physics. It is given with a special variable little g. So little g will be equal to positive 9.8. We're just worried about the size in this case, not the direction, the negative sign. Little g is 9.8. Number 6, the idea that all objects have the same acceleration due to gravity. In other words, the same acceleration as they fall to the ground. It's surprising to some people. Let us try to clarify some things at first. First of all, I'm not going to try to say that as you drop a piece of paper in the classroom, it accelerates downwards just as fast as a rock. That is not the case. But the acceleration because of gravity by itself, that's going to be the same. You might be thinking, what's the difference? Well, here we go. Number 7, this value, this 9.8, this value is the acceleration due to just one single force, the force of gravity. Other forces may be acting on an object to change the acceleration during a fall. The most noteworthy of this is the force of air friction. Air friction is the reason that a piece of paper will fall more slowly than a piece of rock. If we remove air from the room, then all things fall at the same rate. So to prove that, I'm going to show you a little video. So here we have a tall tower. It must be about 50 feet across and maybe 200 feet high. It's huge. They used to use it to test out spacecraft. They would suck out all the air from this thing and test spacecraft out. And they're hoisting up on the crane here some ostrich feathers. They're about 3 feet long, maybe 2.5 feet, and a big bowling ball. Okay, so the bowling ball fell faster here, but that's because they haven't sucked out the air yet. You may have noticed that there's a person standing in the room at the same time. Now we have it in a vacuum. Notice that the feathers are not fluttering at all because there's no air pushing on the fibers. Okay, so without air friction, everything falls at the exact same acceleration. The astronauts, when they went up to the moon, they did a very similar thing. Okay, so um, NASA knew that high school students all over, literally all over the world, study this idea of no air friction, everything falls at the same rate. Demonstrating this in a high school classroom is very difficult. People tried to do it by having these glass tubes that were about 3 inches across. They would put in a feather and a little rock or a marble or something like that. Then they'd seal up the ends of the tube and suck out all the air. And then they'd try to flip the tube one way or the other and show that the two objects were falling at the same rate. It was not very effective. The feather would drag on the sides of the tube and slow down, or it would get stuck to the marble. It was not very satisfying. And so they purposely took a little feather on the trip to the moon to do this demonstration. So obviously there's no air on the moon, right? Remember that? So in his left hand or right hand here, we can see that he has the hammer. It's upside down right now. And then over in his other hand, he has the little feather right there. Feather, hammer. And they hit the ground at the same time. See that again. And again. Okay. Ah, number 9. This is not to say that the force of gravity is the same for all objects. The force of gravity on an elephant is greater than the force of gravity on a feather. However, the mass of the elephant is also obviously much greater than the feathers. The bigger mass and the bigger force cancel each other out to result in the same acceleration as the feather. Number 10. All of our work in this class will assume that air friction is not significant. This assumption is not always true, but it makes things easy enough for us to calculate. Number 11. In this course, phrases such as an object is dropped or an object falls, that will always mean that it is released with an initial velocity of 0. So you'll always be able to write down that v sub I, the initial velocity or the starting velocity, is 0 meters per second. Now you'll also see other phrases like an object is thrown down. Okay, that means there is an initial velocity. So VI will be like -15 or -10, some negative number, meaning that it's downwards velocity. The phrase, how fast does it hit the ground, means what is its speed when it first starts the squishing process of the impact, when it first starts to make a dent in the ground. It's still moving. It does not get to be 0 until the very end of the impact, but that is a measurable amount of time. It might be 5 milliseconds or something along that lines. So we want to know the velocity just as it starts to slow down. Do not say that how fast does it hit the ground? It means that it's 0 because it's stationary. No. That's at the end of the hitting process. We want to know the speed at the beginning of the hitting process. Think of it this way. If there was somebody who was very unfortunate and they drove their car into a tree and they were sent to the hospital, one of the questions that you might have is, well, how fast did it hit the tree? Were they going 55 or 20 or whatever? Nobody would ever say, oh, well, no, obviously they went 0 because the car is stopped. No. Hitting a tree at 50 miles an hour is a whole lot different than 20 miles an hour. And so we would just say, how fast did it hit the tree? In the same way here, how fast does it hit the ground is the velocity before it starts to slow down. Number 13, derive a new equation for dropping objects. Rewrite one of these equations to give you the time of an object being dropped a certain distance. This will be called the time to drop equation. Simplify to have just one number in the denominator. Do not have 9.8 in the final equation. Okay, so here we go. This is how we're going to do it. We're going to start off with the long equation. And then we're going to subtract off the x sub I from both sides. And so that gets us x sub f minus x sub I equals, these cancel out. VI, the initial velocity of an object being dropped is 0. It's still multiplied by t. For the acceleration of a falling object, we put -9.8. Let's simplify this some more. X sub f minus x sub I. Let's draw a picture of that. We have the ground here, so that's the origin, and that's going to be the final location, x sub f. The initial location is something way up here. It's where the object was starting off before it starts to fall. That is the height of whatever it is. So if on the left-hand side here, I have x sub f minus x sub I, that's going to be 0 minus whatever the height was. 0 minus the height. 0 times time is going to be 0 no matter what. Half times negative 9.8 is negative 4.9. And then we still have our t squared. Now, I hope that you would accept that in both of these cases, the zeros are not important. They disappear. I'm now going to divide both sides by negative 4.9. On the left-hand side, the negatives cancel out, leaving just the h over 4.9. On the right-hand side, the negative numbers disappear and we just have t squared. I want to get t by itself, and so I'm going to square root both sides. So I have then the square root of h all over 4.9 is equal to just plain old t. The square root and the square cancel each other out. And then just to make things look more pretty and normal, we flip-flop it, and we have t equals h all over 4.9. That is going to be called the time to drop equation. Now, there are other forms of this. You'll see this in other textbooks, other websites, as t is equal to square root of 2 all over g, for instance, times the height. Or t is equal to the square root of 2d all over g. Remember, g is 9.8, and so 2 over g is the same thing as 1 over 4.9. Anyway, you could have a d there. You might have a y for the vertical height. There's several different versions of it, but it all boils down to basically the same thing. And we're just going to have this version because I think it's the easiest way of doing it. H for height. Number 12, as h increases by doubling and doubling and doubling, what happens to the time? Does it double and double and double? Actually, no, it doesn't, because the h is in the square root. So the t does increase, but more slowly. It does not double and double and double, but it does increase. Number 13, there is a strange belly flop competition in Norway. People flop from a 10-meter high dive. That's 30 feet. That's about the height of a 2-story building, maybe even a little bit more. How much time does a person fall from this height? Okay, so looking at the numbers, well, let me erase this here so that it looks a little bit better. Okay, 10 meters, that is the height. How much time? We are looking for the t. Is there anything else that we need to know? Not really. We can go right to the equation. T is equal to the square root of h all over 4.9. Put in our number, 10 all over 4.9. That's going to be t is equal to the square root of 2.04. The square root of 2.04 is 1.42 seconds. Almost a second and a half of falling down all the time. I'm sure they are thinking, why am I going to do this? This is going to hurt a lot. Splat. Number 14, how fast does the person land on the water? Okay, well, we have to think to ourselves, how fast? We are looking for a velocity of some sort. Well, is this going to be the initial or final? No, this will be the final velocity. But we know that the initial velocity is 0 when they're standing on the diving board. So if we find the final velocity, that's the same thing as the change in velocity. So either one of these would work out. we are looking for that. We know the time and we know the locations. We also know how fast or what the rate of acceleration is. And so I could use this equation right here. The acceleration is negative 9.8. The delta V is what we're looking for, so it stays a letter. And the T is 1.42 seconds. Multiply both sides by 1.42. And the answer you get is negative 13.997 meters per second. That's how much you change the velocity. Well, if you start off at 0, then the final velocity is that much too. Negative 14 meters per second. That's about 30 miles an hour that you're slapping your belly against the water. That's going to hurt. Number 15, Billy Bob drops a rock down a hole. He hears it hit bottom after 3 seconds. How many meters deep is the hole? So in this case, we are given the time. And we want to know how many meters. We want to know how high he was. So we're going to use the equation, but we're going to use it slightly differently. The T gets the 3, and the H stays a letter. So how do you solve for H here? You want to get the H by itself. The first thing you're going to do is square both sides. Three squared is 9. And then the square and the square root cancel each other out, leaving just H over 4.9. And then you multiply both sides by 4.9. I don't have a calculator handy, so I'm going to have to do it off to the side here. Long way. 36 plus 8 is 44. So multiplying both sides by 4.9, we get H is equal to 44.1. To double check that, I could say that this is almost like multiplying 9 times 5, which is 45. So that's doggone close. I'm going to say that's probably right. And that's the end of the notes.